So for this video, I want to go over the susceptibility analysis and some of the calculations for the MSE 407 Lab 3 on high temperature superconductors, particularly YBCO. Okay, so I'm here with the handout that I gave everyone, and if we sort of scroll down to the part about susceptibility. So this is in the fourth meeting. So this is determination of the critical temperature. So that's what we want to do with this measurement. That's one of the many things that we can get out of this measurement, but the most critical portion of this is the critical temperature, TC. That's what we want to get out of this measurement for our pellets, and what sort of conditions from the procedure that we did may affect the critical temperature. So that's what we're going to do with these calculations, is we're going to try to get the critical temperature, and we're also going to see what other kind of information we can get. So just kind of a review, you should have watched the susceptibility procedure video to see how it was actually run. But I just want to go over some of the aspects here, and particularly I want to go to the sort of the schematic here for the circuit. So you saw the function generator where we apply a given frequency of AC sinusoidal voltage. So that's and that translates to a voltage into the system. It goes through a resistor R1, which was 55 ohms about for our system. And then we have our inductor L, which is our copper coil, which has our pellet inside. So our copper coil creates a magnetic field within the coil, and it is an inductor, right? So you might have heard of it as a solenoid as well. It goes by a number of ways. But this is the voltage of across the inductor, and that's what we're trying to measure in this case. And we also can look at the current as well. So that inductor is what we see here. So for our setup, we basically have this Teflon housing that you saw in the video, and we wrap those coils around it in 1,000 turns for our specific example. And when we pass an AC current through this, it will create a magnetic field within the coil, which is then interacting with our pellet, right? And we saw with the levitation experiment, the interaction was it levitated the magnet because it was diamagnetic, and it opposed the magnetic field. So here, if the same happens, if our pellet kind of expels the magnetic field, then we measure it in the circuitry, its effect on basically the inductor. And so that's what we're trying to get. So we basically want to look at what happens in the circuit when we go through this transition, as opposed to comparing that to when there isn't a pellet there. So that's what we're going to look at with this video. We're going to sort of analyze, and we're going to look over the data, see what we can get out of it, and see if we can get the critical temperature. I want to draw your attention to the appropriate calculations here that we may need to use. And so in that same section, you can see the inductance is described here. And so just to kind of go through this, the inductance is the omega L. And then we have VL, so that's the voltage of the inductor L. And then we have current I. And then the resistance is the resistance of the coil. So this is DC resistance of the inductor or the coil. So we'll talk about this. And then there's also susceptibility, which is kind of the name of this unit, which is actually approximated with this formula. So we look at the inductance at a point over the inductance above TC, so kind of the average inductance above it. And then we also have to estimate the fraction of the coil volume. So that's kind of important things to look at, because susceptibility tells us some information about the superconductor, because an ideal superconductor will have a magnetic susceptibility of -1. So it basically completely expels the magnetic field within it. So that's important, and that's why we typically want to get the magnetic susceptibility. All right, so I'll pause here and we'll sort of transition over and we'll start to look at the data and see what information we can get out of it, what it looks like, and how to sort of process and analyze this data. So I've got some sample data here that I want to sort of go over with you and show you what everything looks like. And I'll start with this file. Again, this is not your specific data, just some example data run under similar conditions. But the three types of data I want to show you is the DC resistance, here it says the frequency 250, which is what we used in the experiment, but it says blank. So this is basically a run that we did, but without a pellet. And then we have the AC run with the pellet, which is the test. So I want to go through those three sets of data. And I want to show you the DC first. And if I just kind of plot this, I'm going to plot the temperature and the V over A. So here, there's no pellet in this. It's just looking at the coil. So I'm just trying to figure out what's happening to the coil as a function of temperature. And so I'm going to use the outside temperature because that's the one hooked up to the temperature, or sorry, that's the one right in touch with the coil. And then I'm going to look at V over A. V over A, in this case, if it's DC, this means resistance, right? So if you look at your sort of Ohm's law, that's resistance. And so I'll just highlight those two. And the first thing I'll kind of let you know is that the way that we're collecting data, the last one is actually always 0. And so you can actually kind of ignore that last point just so you don't have to deal with that 0. It's just in the way that we collect the data. It's nothing with the actual experiment. It's just how we're sort of collecting the data. So, and if you're curious about that, you'll notice the temperature here as 80, 80 and a half, 81. So it doesn't actually record points only at 80 and then 80.5. We take all of the data that's given to us and then basically bin it or divide it into these half degree temperatures. So that's and in the process of doing that, we end up getting a 0 for the last point. So, but this just makes it easier to adjust everything that we have. So if I just plot this, it looks like it's having some difficulty now. There we go. Okay. So let me go back then. Go back up to the top. And I'm going to ignore that last point. And I'm going to insert a chart. So this is Google Sheets. If you're using Excel, things will be slightly different. But and here, one thing you'll notice is that we actually had some difficulty with the thermocouple on this run. You'll have a cleaner data set to work with, but these first few points are actually not great. So you can actually kind of forget those as well. So just kind of ignore these points for now. But essentially what you see is that it's fairly consistent. It's a fairly linear curve. And it turns out if you get rid of those points, and I've got it down here already, it's pretty linear. And not exactly, but it's quite linear. So what this is, like I said, is V over I and DC is resistance. And so what we're measuring here, without the presence of a pellet, is we see that the resistance, so let's look at this one, the resistance goes up pretty steadily with increasing temperature and K, right? So if you think about a metal, right, the resistance will increase with increasing temperature, or the resistance will decrease with decreasing temperature, right? And so this is what we're seeing in this curve. So that's something that we have to consider when we are running this experiment, that the resistance of the coils themselves can increase with temperature. And so we have to kind of sometimes account for that in this experiment. All right, so that's the first part. And we might come back to this, but I just wanted to show you the DC run, what that looks like. All right, so let's look at now the AC run with a frequency of 250, which is what we used for all of the experiments. So here, I'm going to look at the inside temperature, so the temperature that the pellet would be at if there was one, and then I'm going to look at V over I for this. And so again, this is AC current, so it's no longer resistant. This is the AC component of it. And so let's look at a chart of this. And again, I included that last point, so let me get rid of that. All right. So yeah, that last point is just always always 0. All right. There we go. All right. So this, it's not plotting it very great. So I'm going to go ahead and click on this so that I can adjust and put, looks like 35.5. And I just want to see kind of what it looks like. So here we see that the impedance, or the AC resistance of the circuit, looks different. It's no longer just a linear line because we have the inductor involved. And this curve isn't ideal, which is why we're having some difficulty this year with these measurements. So I'll go over everything, but just to kind of foreshadow things, we're having some difficulty with these measurements. So, but again, this is a different signal, right? It's no, you can see it's no longer linear when we look at the inductance as a function of temperature. But this is, again, without pellets. So this is what it would look like with nothing happening. So just the inductance as a function of temperature. All right. So now let's go to the test run. And so this is our sample. And again, I'm going to use the inside temperature because that's the one on the pellet. And I'm going to look at the V over I. So, and we can see how this compares to the sample we just looked at with no pellet. So again, I'll insert a chart. And I'll have to adjust this again. There we go. All right. So now you see that something else has happened, right? So there looks like there's something here, a change in slope. I apologize for that. In the region between 90 and 100, right? But otherwise it has the same kind of similar, you see that there's a slight decrease here, and then it kind of has the kind of parabola-like shape up here. So the curve has been changed here. So basically at around this point, this is kind of the onset of superconducting properties, right? If we are decreasing the temperature, this is kind of the onset, and then it continues to do so until around the 90 range. So this is kind of the difference from no pellet to pellet. So the pellet has kind of this influence in it. So let's actually plot these together. So I'm going to get rid of this one for a second and just show you what it looks like with the blank versus the one with the pellet. So I've got the, so I'm going to just do it over here. And extend this all the way down. And then we have our blank run, so AC with no pellet. And I'm going to use this data. All right. And then I can also plot the DC for that, but I'm just going to look at these two AC ones real quick. All right, and then we need to change this again so we can get a better picture of it. And so here you see, kind of see what's happening, right? This is the red is the no pellet. So this is kind of the response, what it looks like without any pellet. That's just kind of looking at the inductance. And then, so you see the shape of it is identical in this position above 100, and then down here it's very similar as well. And then the difference you see is with the pellet, you see this drop, right? So this is the response of the superconductor. And so we're going to do kind of a modified analysis of this because we're not able to calculate susceptibility directly. And again, this is from some of the challenges with this experimental setup that we're having. So it's nothing that you did. We've just looked at this data and we're not able to calculate the inductance directly, and we're not able to calculate susceptibility directly. So what we're going to do is we're going to compare the blank run to the run with a pellet, and we're going to basically subtract. So basically we want to look at if we subtract the blank from the one with our pellet, we'll basically be able to highlight the change that occurs, and that's what we want to do. So that's what I'm going to do here. So I've actually already kind of done it here. So if I subtract the AC run at 250 hertz minus the AC run at 250 hertz with no pellet, I'm going to get this. I think it's already correct, but let me extend it just in case. All right, and I'm going to plot that. And again, I'm going to forget that last point. Insert a plot here. And there's going to be a lot of other series that we can just delete. Oops. I think I have to delete it here. Okay. So I'm just going to delete all these other series, and I'm just going to look at the subtraction. So here's our subtraction. So what this does is it shows that above this point, around this point, there's really no change in the signal. So it's kind of flat. And you see down here, we've kind of reached a steady state as well, but it's much lower. And there's this transition region, right? So we kind of have a roughly steady state down here, a flat region, and a roughly flat region up here, and then a transition, a slope. So this part tells us the critical temperature. And we can also get some information about the height, so the difference between this plateau and this plateau down here. And we can also get information about the range of temperatures over which there is a transformation. So those are the three things that we're going to look at in these calculations. So we're going to look at the transition region, the range. We're going to put one number to this transition as well. And we're also going to look at the height. So the difference between this signal and this signal down here. So those are kind of the 3 points we want to get across. All right. One other point before we get to looking at the critical temperature and the width and the height of that transition region. And that has to do with the temperature itself. So you'll notice that the lowest temperature we record is 80 degrees K. This is not, in fact, the lowest temperature that we measure. The lowest temperature we actually measure is 79, so 79 K. So the lowest temperature we measure should be the boiling point of liquid nitrogen, because we're filling this thing up with liquid nitrogen and we're basically allowing it to come to the lowest possible temperature. So our lowest temperature is 79, yet the boiling point of liquid nitrogen is 76. So this is something that you can look up in the literature. And so we notice that there's always this shift between the lowest temperature we measure using our T-type thermocouples of 79 and what it actually should be, which is 76. And so that's a 3-degree offset. And so we are going to correct for that by basically shifting that by 3 degrees. And so we have to shift it down 3 degrees. So we're going to take our temperature and then subtract 3. And again, that's because we're measuring 79 with our instrumentation when it actually, in fact, should be 76. And so we're going to do a uniform shift of 3 degrees. And so I'm going to go ahead and correct all of these values. And you just see that it's offsetting everything by 3. So that's how we're going to approach this correction. So that's an assumption that we're making, is that we can shift it by 3 degrees. And so everything else, though, would be the same. So this is just the difference between the measured and the real temperature. And so we're going to still use this AC minus the AC with no pellet. And so now if we plot this and then make a chart, and again here, the shape hasn't changed. Oh, having trouble moving it. Okay, here. The shape hasn't changed, but you can see that the lower temperature has changed. So this is going to be important for measurement of the critical temperature, right? Because we want to get the accurate critical temperature. We don't want to get something higher. So in this case, if you don't do the subtraction, everything is going to be shifted to 3 degrees higher. And in superconducting properties, right, the higher the temperature of the superconduction is, the better, right? So if we don't have this correction, we're actually falsely stating that our superconductor is 3 degrees better than what it should be, and that's an important distinction to make. So that's just a point we want to make about the temperature correction. So we've done the temperature correction. Let's look at this curve again. So this is what we've produced for our YBCO pellet, subtracting the AC voltage of the inductor over current, and then the AC voltage, same voltage over current with no pellet, and we produced this as our difference, right? And we've corrected for the temperature difference between the recorded lowest temperature of the thermocouple and the actual temperature based on the liquid boiling point of liquid nitrogen. So the 3 things that we're looking for, like I said before, are going to be the critical temperature, and then the width of the temperature width of the region, and then the height of the difference. So the critical temperature is typically taken as the midpoint between the inductance above and inductance below. So we're going to use that practice here. So this value, as you can see, if you can you can fit a line to this too to get it a better, but essentially this is negative 0.2. If we just kind of go through all these values, it's roughly negative 0.2 is what I'm going to take that value as. And so if we're looking for the midpoint, we want to get the midpoint between this and this. And so this down here is about negative 1.4. So the midpoint of this would be about negative 0.8. And so you can fit a line to that. So you can draw a line in here and get a better fit. But I'm just going to kind of go to 0.8 and show you what that might look like. And so it's somewhere right here. And you can see that this is the closest one I can find of negative 0.8, so halfway in between, and we have a temperature of 91. So for this analysis, our critical temperature is approximately 91. So you can get a better fit, more consistent by fitting these regions, but I'm just going to take 91 to be our critical temperature for this demonstration. All right, so that tells us the critical temperature for our superconductor. We have an onset up here at around 94 or 94.5, one of those values, and then we have the slope stops changing around this this value here of somewhere. So if you just kind of fit this line, then this point right here at about 84 is about where it stops changing slope. It's a little hard to see, but about 84 all the way up to 94, right? So this tells us that the temperature width over which that transition occurs is 10 degrees, right? Or 10 K. So that's another important region. We typically want these transitions to be very sharp, And so knowing how wide that transition region is important. So this, in this case, it's 10 degrees. So we've got the width of 10 degrees. We've got the critical temperature halfway in between the lower and the upper plateaus at 91. And then our drop in signal from here to here, we've already actually got that, right? So we saw that this is negative 0.2. This is negative 0.4 roughly. And so our drop is 1.2 ohms in this case. And so this can tell us about how much of the signal is being expelled from the superconductor. So this can tell us about the properties of the superconductor. So let me just write those out down here. So TC, we approximate, and this is in Kelvin, was 91. The temperature range was 10, right? It's from 80, that was 84 to 94 approximately. And then the height, which is in ohms, if you look at the y-axis, that height was a magnitude of 1.2 ohms approximate. All of these are approximates because I'm just pulling them straight from the curve. You can get more consistent results if you fit these areas and so forth. So these values are important information to kind of compare between your different series to see if anything changes here. So does the transition range change between one pellet and the next? Does the critical temperature change from one to the next? And does that height change as well? So since all of our pellets are approximated to be roughly the same size, then these are kind of valid qualitative comparisons that we can make. Ideally, we would want to have the actual inductance and the actual susceptibility, but like I said, we're having some issues with the setup itself and the way that we're collecting data, and so we're able to do more of a qualitative comparison between the properties. So that kind of concludes what I want to show you with susceptibility. So these are kind of three quantities that you should be able to calculate for your YBCO pellets that you have made or we've made in this lab. And so you can compare and see what the trends are with any of these properties with the different conditions that we've done.